Hello, welcome to the course Electronic System Design. Last lecture we saw one example where we took the summing amplifier. This circuit will add up 4 signals V1, V2, V3, V4 and produce the weighted output of these inputs, the 4 inputs, and we can have simple algebraic sum V1 plus V2 plus V3 plus V4, or depending upon the resistance values we can choose all these resistance values in some ratios and we can produce the weighted sum as well, V1 plus 2 V2 plus 3 V3 and so on, whatever we want to provide. So, this summing amplifier we started from the very scratch where we have 4 inputs, 1 output. This is the requirement of our system, and we go for a particular op amp, whatever is available in KiCad or whatever is available in the market. So, we pick a general purpose op amp, produce the schematic using all other resistance values, and then assign the footprint and create a complete PCB, which was a single layer PCB. Single layer PCB means all the traces, whatever the connections we need to make, they are all available on the front layer itself. So, the processing of this PCB, the fabrication steps required for this PCB are much less compared to the complicated PCBs where we have multiple layers to fabricate. So, single layer PCBs are very easy to fabricate, the cost is also less. However, the circuit complexity also should be less to provide only on single layer. If we have the complexity which is little higher, then it is not possible to provide all the connections using single wire. There will be some cases when the trace is coming from top to bottom and we need to write a trace from left to right. So, there is no way we can route that trace, because if we produce both the traces on the single layer, they will touch each other, they will cross each other, and that intersection there will be a short circuit. So, if our graph of the circuit is not planar, then we cannot route all the traces in a single layer. That time we need to go to the second layer, or sometime it is not possible even in the second layer to route all the traces. That time we go for multiple layer, 3, 4, 5, even up to 20 layers of PCBs people can make, and they can be designed by many manufacturers up to 20 layers PCB. These are common in the industry. So, today we will go one more example, and today we will use a 555 timer IC, which is very common IC students use in the projects. So, this 555 timer IC which we are going to use, this has 2 modes, one is the monostable mode and one is the astable mode. Monostable mode, as the name says, this has only particular stable state and this will stay only in that state or the other one. So, that is monostable state. The astable state is where the output is continuously toggling from one state to another, and automatically the signal will be generated, something like a pulse waveform will be generated because of this astable nature of timer IC. So, today we will have this as an example. So, we want to make a circuit which is astable vibrator or multi-vibrator. We want to produce a square wave using this 555 timer IC, and all the necessary components whatever we need, that will be using in the schematic. So, let us go to the software how to start this circuit. So, this is the software window. So, we go to the file and create new project. We give it a name, let us say example 4. When we save this, these 2 files will open up here in this dialog box. We go to the schematic editor. Once we click on this schematic editor, This is the schematic sheet where we need to import all the components whatever we are going to use. So we are going to use today the 555 timer IC. So let's look out for any particular 555 timer. We press on add symbols. This choose symbol dialog box will open. So it says there are 21,103 items are available for us to choose, which is a very good number of components which are already available to KiCad. However, still if we do not have that particular symbol, we can always import from the manufacturer website and include that into the software. So in this dialog box, we write 555, which is standard 555 timer IC. So we choose any one of these timer IC, for example this LM5 XM. If we click on this, the short description says this is a timer IC 555 types compatible SOIC, which is the form factor of the package. If we see on the right, we have the symbol available to us where we can make the schematic, and also we have the footprint available for this device. So this is very good for us. We need not to create the footprint for this particular device, or we need not to even import from the manufacturer, it is already there. So symbols and footprints both are available, so we can use this IC if this meets our electrical specifications. For the electrical specifications, we go to this area where it says the name of the IC LM5 XM. This is derived from this standard 555 timer IC, which is precision timers. This is the footprint information. This is a package. These are the dimensions of these packages. However, the detailed footprint information and electrical specifications are available in the data sheet, and the data sheet is also available at this link. So all these informations are available in this choose symbol window itself. We click on this and it will lead to the data sheet of the components, which is very important to check whether this component is suitable for us or not. So we click on this link and it will lead to LM555 datasheet from the manufacturer, which is Texas Instruments. So once we click on it, this will open up the data sheet, which looks something like this. It says the manufacturer is Texas Instruments. This is a LM555 timer IC. There is a short description to this IC. The LM555 is a highly stable device for generating accurate time delays or oscillations. Additional terminals are provided for triggering or resetting if desired. If the time delay model of operation, the time is precisely controlled by one external resistor and capacitor. So this is the description. Any designer, whoever want to use this, can design and go through this document. So these are some features available of this particular timer IC. This is the internal diagram. We need not to bother about this internal diagram. This is the manufacturer who designed this IC using these components. We go down into this data sheet. This says that we have this IC and there are 8 pins to this IC. Pin 1 is the ground terminal, which is written here. Pin 2 is the trigger terminal. Pin 3, these 1, 2, 3 naming, this is the physical pin available on the package, and this pin 3 is the output pin where the output will be generated. Pin 4 is the reset, pin 5 is the control voltage, pin 6 is the threshold voltage, pin 7 is the discharge, and pin 8 is the supply voltage. So if we see, the pin 1 is the ground and pin 8 is the supply voltage. This is where our supply will go, positive supply and ground, and all other pins are signals which will be generated by this 555 timer. These are the pin functions given in the table. So pin number 5 is the control voltage which controls the threshold and trigger levels. It determines the pulse width of the output waveform. An external voltage applied to this pin can also be used to modulate the output waveform. And this pin is input type. So this is the type of that pin I/O, whether it is input pin or output pin. So this pin is an input pin. It means this pin need to be driven by external circuit. Whatever is we are going to attach the component, the external circuit need to provide certain voltage which we apply on this pin. The pin number 7 is a discharge pin, which is again input type, means we want to apply input on this pin. This is an open collector output which discharges a capacitor between intervals. The pin 1 is the ground pin, which is output type, ground reference voltage. Pin number 3 is the output, which is output type. Pin number 8 is V plus, which is the input supply voltage with respect to ground. So these are the pin functions given in the tabular form. For in-depth knowledge of the circuit, we can always go to this data sheet and figure out the electrical specifications of the component. These are some reliability ratings. For example, the absolute maximum rating for these devices, which is given here. The maximum power dissipation for this particular form factor is 613 milliwatt for this particular form factor and 1180 milliwatt for these particular form factors. Soldering information. So when we do the soldering of these packages, we should not exceed 260 degrees centigrade for 10 seconds for PDIP type of package. For SOIC package, which we are going to use here, for 60 seconds the temperature should not exceed 215 degrees centigrade. So these are some reliability ratings. These are ESD ratings. So any ESD zap should not be greater than 50 volt in HBM model, which is human body model. Recommended operating temperature is 70 degrees, up to 70 degrees maximum. Minimum is 0 degrees. So between 0 and 70 degree is the recommended operating temperature. Supply voltage is 18 volt maximum. So we cannot apply any voltage higher than 18 volt to these ICs. Junction temperature is limited to 70 degrees. These are electrical specifications which we need to carefully check while designing any schematic or PCB. So if we have more than one components, the supply voltage should be compatible, or all the components should be compatible to the supply voltage what we are choosing. So here the parameter supply voltage, the minimum voltage is 4.5 volt, which we need to provide at the pin 8. The minimum is 4.5. We cannot go for 3 volt power supply or 1.8 volt power supply. We need to have minimum 4.5 volt power supply, and the maximum voltage we can have is 16 volt at the power supply. Our power supply, the current is 3 in the typical case, however the maximum current is 6 milliamp. If we are using VCC is 5 volt, the supply voltage is 5 volt. If we are using supply voltage as 15 volt, then the maximum current is 15 milliamp. So this current depends on how much voltage we are using, and we have this voltage range of 4.5 to 16 volt. We can choose any voltage in between and our supply current will change accordingly. So whenever we design the circuit, we need to first decide our supply voltages and choose the component accordingly. These are other parameters which are given in this electrical sheet, which may or may not be directly limiting our schematic design. So whatever is needed, we need to go and check in the data sheet. These are some performance graph of these ICs. Sometimes these are very important to check. If we go down in the device functional modes, there are 2 modes specified for this particular IC. One is the monostable mode, what we just discussed. In this mode of operation, the timer functions as a one shot. The external capacitor is initially held discharged by the transistor inside the timer. Upon application of a negative trigger pulse of less than 1/3 VCC to pin 2, the flip-flop is set, which both releases the short circuit across the capacitor and drives the output high. So as the name says, this will provide only one transition based on the capacitor charging. Once the capacitor charged, it toggles the output when the voltage across capacitor reaches 1/3 of the power supply. That time it triggers the output, and only once it happens. This is the monostable mode. If we go to the another mode, which is astable operation, the circuit diagram is something like this. We have this LM5 IC. Here we connect the external circuit as per this connection. Here if we see closely, we have this output power supply connected to 8 and 4 pin of the package. From this power supply, we have a resistive ladder coming in, which is RA and RB. So this RA is connected from supply to this intermediate node or pin 7, and this RB resistance is connected from pin 7 to pin 6, and one capacitor is connected, which is C, from this pin 6 to the ground, which is pin 1. So the mode, in this mode of operation, actually this capacitor will keep on charging and discharging, and whenever it discharges and charges, there is a particular threshold values. Whenever capacitor go below this point, the output triggers to 0, and when capacitor voltage rises above this trigger voltage, the output toggles to high, and this happens automatically. This capacitor is keep on charging and discharging, and the output will keep toggling between low and high. This will produce a pulse at the output. So if we go down, this graph is also given. This is the capacitor voltage which is charging and discharging. Here it is charging and here it is discharging. So while charging, the output is high, and while discharging, when the capacitor reaches the trigger voltage, immediately output will be pulled down and capacitor will start discharging. When the capacitor here hits the lower threshold voltage, again the output is toggled to high voltage and the capacitor start charging. So this happens charging and discharging continuously, and the output is continuously pulled up and down, it will produce this pulse at the output. The relation between the various information, timing information is given here. The T1, the charging time, the output high, is given by 0.693 times RA plus RB into C. So, this RA resistance and RB resistance we add up together, multiply by C and multiply by 0.693. So, this is the charge time or the time where the output is high. This time is given by this expression, and the discharge time where the capacitor is discharging or during which the output is low. This time is given by 0.693 times RB into C. So, on time or the high time of the pulse is determined by this equation, and low time when the output is low is determined by this equation. We can choose values of RA, RB and C accordingly and provide and produce any kind of pulse waveform using this 555 timer. Now, the total time period is T1 plus T2, on time plus off time, which is this. The frequency of oscillation is nothing but 1 upon total time, which is 1 over this expression. This comes out to be this. So, if we want a duty cycle of 50%, for example, we want on time as equal to off time, we can equate all these equations together and find out the value of RA and RB, whatever is suitable to us. We can produce a nice square waveform. So, this is how this 555 timer actually look like. Let's go to our software and try to make this as stable circuit in the schematic and the PCB, and see how it look like when we make the PCB of this complete circuit, which is a stable multivibrator. So, here we see in this schematic we have this LM555 component, and the external components what we need is RA, RB, this capacitor need to be there, and this capacitor, which is 0.01 microfarad capacitor connected from pin 5. These are connected through dotted 1, so we can ignore for time being. We will not use these components. So, we use only this component LM555, 2 resistances RA, RB and 2 capacitors. So, this is all the components what we need to create this PCB. So, let us go to the software. We close this datasheet and choose this particular component and click on OK. This symbol will come on the schematic sheet. Click on it and press escape. Now, this symbol is available for making schematic. So, as a rule, the very first thing we do, we put the supply and ground connection. So, we go to this add power and select VCC. We put VCC, then again press on this and write G and D, which is ground. Yes, anywhere, and the ground will appear. Now, we press escape to leave this add component option and have the wire to connect these supply to the symbol. So, we click on this and click on ground. So our symbol now has VCC and ground connection. Next is we need to have the connector to provide these power supply and ground supply. So we again go back into add symbol option and choose the connector, and we want two pins, one to provide ground and one to provide the power supply. So we go for one array of two connector. So we can choose this, which is con 01 cross 02, which is one array of two pins. So one pin we can use for VCC and one pin we can use for GND, the ground connection. We click on this and this is our connector. We route the wire from this pin, pin 2 to ground, and this pin to the VCC. Now we need two resistances and two capacitances. So we go back again into add symbol, we press R and choose this resistor. This is general purpose resistor and there is no footprint specified as a default. We will choose this symbol and later on we will specify the footprint as per our requirement. So we click on OK and put two values, put two resistances, again we need to put resistance, so we put one more instance of resistance. So this is R1 and R2. We have two resistances, which is R1 and R2 or RA and RB. We need two capacitance as well. So we go to choose symbol, write C. This is the capacitor symbol. We will take this and put here. This is capacitor 1 and let's say this is capacitor 2. We put here. So these are all the symbols we need for our design. Now let's connect them together as per our schematic. So the RA, one terminal is connected to the power supply. So we connect this terminal to power supply. Another terminal is connected to RB as well as the pin 7. So this pin 7, which is discharge pin, is also connected to the midpoint of RA and RB. The pin another terminal of resistance R2 is connected to this capacitor, and this node is also connected to pin 6 as well as the pin 2, which is the trigger terminal of our IC. So we connect this as well. So here again we have routed this wire and there is no dot, green dot here as well as here. It means this wire is not connected to any of this supply or this intermediate wire. This is connected only here where this green dot has appeared. So this is the connection of this wire with this routed wire. So this green dot says that there is a connection in the wire. So this is how we connect the pin 6 to pin 2, the other terminal of this capacitor is connected to the ground. So we connect on this ground. Next pin is pin number 5. This should be connected to a capacitor, and the other terminal of this capacitor is connected to the ground. The pin C, the pin 4, which is R, is connected to the supply voltage. So our circuit is now complete, where we have connected all these components together as per our specification. We click on this, and this is our complete schematic, where we have connected RA, RB and C as per our specification, and this capacitor will be automatically charging and discharging through R1 and R2, which is our RA and RB in the schematic. We can choose the values of these R1 and R2 and value of C, and we can control our frequency of operation. This pin Q is also there, however we are not connecting it to any other component. This pin is left behind, which is not usable to us right now. So we need to provide a no connection signal here, so that the schematic knows that we are not going to use this pin, and it will not flag this as a error. So there is a option of adding no connect flag. So we click on this and we put a no flag, no connection flag here. So when we say this, that we are saying software that we are not using this pin in our schematic. So now our circuit is complete. The next step is to assign the footprints to all these symbols. So for LM555 we already have a predefined footprint. For rest of the symbols we need to attach the footprints. So we go to this option, assign footprints, click on this, and all the symbol list will appear here. At line number 6, which is LM555, we already have a footprint assigned, so there is already an entry here. For rest of the symbols we need to provide the value of these footprints, which will be taken by software as default. So we click on the capacitor and we go to the capacitor. So there are 3 types of capacitor library available. One is the capacitor SMD, which is the surface mount device, and these are tantalum capacitors, which are against surface mount device. And the third is the capacitor THT, which is the through hole capacitor. So for time being we will use, let's say, through hole capacitor. We can use any of it as per our parts availability. So for this example we go for the THT, which is through hole capacitors, and these are all the footprints available for these through hole capacitors. So we can go for any one of it. For example, this is the horizontal capacitor of length 10 mm. So let's say we choose this. We can choose any one of it as per our requirement. So for the example we are choosing whatever is coming. Otherwise it should be as per our specifications of electrical requirements. For the second capacitor we are, let's say, using another capacitor, let's say this one. This is the connector. For this we need to go to connector library. We have this connector, let's say connector TE connectivity. Inside this we have multiple connectors. We want to go for the connector of 2 pins, one array of 2 pins. So we go down, let's say choose this footprint, which is 1 cross 02, which is one array of 2 pins. We click on this and double click. This is assigned. For the resistances, these are R1 and R2. We go to R, the resistance. So again there are 2 libraries, one for the SMD and one is the through hole. So we go for through hole type of resistance, and we need to pick the resistance values. So we can choose any one of it. These are all the footprint values. For example, we use this resistance, double click, this is assigned. For another resistance, let's say we go for the another value, so that we know that what we have put, though it is dependent on other specifications of your PCB. It should not be random. We are doing it here just for the example that we can change it as per our requirement. So now we see in this window all the symbols have their default footprints attached to this. Now we apply save schematic and continue, and then click OK. So now all the symbols are attached to their default footprints. Now it's the time to run the electrical rule check or ERC. So we go to this box, electrical rule checker, we click on this and we run ERC. We click on this ERC. So there are 2 errors again, and the errors same as the last lecture, which says that this pin, the output power pin, is not driven by any power pin. And the other error is, if we click on that error, it will lead to the position of that error. It is saying that this is a power pin, it is not assigned or it's not driven by any other power pin. These are the errors which we understand that we are not using any on board power supply or the battery. So these pins are not driven in this schematic. We will provide these output power and ground through this connector from outside the board. So for time being we can ignore these errors. However, whenever you have the list of error, you need to carefully go for each and every error and find out whether it should be addressed or it should be ignored. So in this example, because we are not using any power supply or battery on the PCB which is driving these power pins, it means we can ignore these errors and proceed for the PCB design. So we can close on this, and this is our complete schematic ready for PCB design. We save on this and click on this switch to PCB editor. Once we click this PCB editor, this PCB editor window will open, and then we import all our schematic here using this button, update PCB from schematic. We click on this update PCB from schematic dialog box will open. We click on update PCB and close. So once we close, this mouse is attached with all the footprints. We can place it anywhere on the PCB sheet, and then press escape. These footprints are now placed on PCB sheet. If we zoom in, then this is how all the footprints will look like. Now we need to arrange it in nice way, because this is just the random placement which software has done. We need to place it properly. So we take this jumper connection, take it to one side. We can rotate it by pressing R. We can place it, let's say, here. These capacitors, we click on this and put, let's say, here and here. So these are the capacitors we have placed, and this is our LM5 IC. We can keep it right here. This is the resistance R2. We can rotate it and put something like this, and this is our R1. We can put, let's say, here. So this is some arrangement. With practice you can do it fast and do it in a more efficient way. If you have more than 10, 15 or 20 components, then it comes with practice. How do we place them each apart from each other and have all these rat nests available. So now we have this PCB to route, where we see all these rat nests, which says that all these connections need to be made, which are shown by this light blue color lines. So to route this, we go to the front copper layer, which is by default in the PCB editor. This front copper layer is already visible here, which is already highlighted. Now we go to this wire, this symbol, which is a route tracks. We click on this and start routing. So we click any point here starting of this rat nest, and wire will start coming in, and whenever we click the next, the last position of rat nest, that rat nest will disappear and the track will be visible. So this is one connection we have made. Similarly, we need to make all these connections. For example, this connection need to be made to this terminal. All these capacitor, this pin need to be connected. So this pin need to be connected here, so we can rotate this capacitor. This capacitor also we need to rotate, so that we have straight wire to connect from this pin to another pin. Next we route this rat's nest. Now there are two rat nests. Now we have a tricky situation. So one is one wire we need to route from here to here, and one wire we need to route from here to here, and if we see these all, both the wires are crossing each other. So we cannot have two traces running on top of each other, otherwise there is a short circuit and our PCB will not work. So in this case we need to route one of the wire into the another layer, which is the back copper. So front copper is here, it is shown by this red traces. So let's write, or let's make the trace for one wire in front copper layer and another we will route in the back copper layer. So we go to this front copper and route this layer. Now the only remaining rat's nest is this, from this terminal to this terminal. This we need to route. So we, let's say, zoom in little bit here. This rat nest from pin 2 to pin 6 we need to route, but we cannot route with this front copper, otherwise it will make a short circuit with this track from 4 to pin 8. In this case we will route little bit of this track in this front layer, and at this point we right click on it and place through via. Through via means we are making a hole in the PCB and taking our signal all the way from the front layer to the back layer, and in the back layer, because this all these red color traces, these are all front layer traces. In the back layer these traces will not be there. We will route our signal through the back layer and will again come back into the front layer after passing this space. So we put the via here. You see, when we have placed this via here, this via appears here. All the dimension of this via we have already specified in the settings of PCB Editor. In the few lectures back, when we discussed the features of this PCB Editor, there are some dialog box preferences where we specify all the default values of these trace, width, the via, hole size and so on. So here now we have placed this via, it means the front layer, this trace is now connected to via, and this via is all the way up to back layer. At the back layer of the PCB this signal is available. So now we go to the BCU, which is the back layer copper, click on it, and then we click on this route tracks and route this track from this place to this place. Once we click here, we see the trace color is blue, it's not red. So the blue color means this is a back layer connection we are making. We click here and again right click, place through via. So we place the via right here again and the via will appear. Now this signal which was in the back layer through this blue color track, this is connected to via again. This via is again from all the way from front layer to back layer. So the signal is available now from back layer to the front layer, and now we can again connect it to the front layer pad. So we go back again to front copper, click on route trace, click on this via and connect this to front layer copper. So this is an example when our graph is not planar, That time we need to go to another layers to route our signals. Here in this case, this red track is going all the way from 4 to 8, and we need to connect this pin 2 to pin 6. For doing that, we first start on the front copper itself, then we dig up a hole and make a via here. Signal will travel from front copper, go through this via to the back side, and in the back side of the board, this signal is traveling from this via to this via, passing this space which is not available on the top layer. Once it reaches this position, again we are putting a via to bring this signal back to the front layer, because the connection need to be made on the front layer. So through this via we are bringing the signal back to the front copper and again routing it through front copper traces to connect it to this pin 6. So this is how multi-layer PCBs are made. We put vias to bring the signal to the other layer. However, we try to design PCB such a way that we use lesser and lesser via. By using vias, there are many complications. If we have a high speed PCB, then my signal actually bounce back from vias because of the impedance mismatch, and we cannot achieve very high frequency operation if we have so many vias in the path of signal. So vias are undesirable, though if we have a complex PCB we need to use these vias if the graph is not planar. So for the critical signals which need to be very constrained in timing, that time we want to route them on the front layer only. If there are some signals which are not so time critical, which are slow moving signals, for them we can use via. So that comes through the experience. First we need to understand the schematic, find out which path is the highest frequency path. We want to route that path on the front copper, and rest of the slow moving signals we can route through vias. So all this comes through experience when we design PCB on the regular way. So now we zoom in. So this is our complete PCB. We can save it and now run the DRC. So whenever we finalize the PCB, the last step is to run the DRC to check out whether there is any error or not. So this is the design rule checker. Click on it and run the DRC. So there is one error which says that the edge cuts layers are not present, means we have not specified the size of the PCB where the PCB needs to be fabricated. So we go to the edge cuts layer and choose this draw a line. We want to draw a rectangle where this PCB need to fit. So this is the actual dimension of PCB which we want to fabricate, the width and length that you can check on the below as well. This delta x and delta y is given. Now our PCB is complete. Let's save it and run the DRC again. For any error, we run DRC and there is no error, zero error and zero warning. So it means our PCB is ready for fabrication. We can have a view using 3D viewer and we can check how it will look like when this will be fabricated. We click on this 3D viewer and this is how our PCB is going to look like when it will be fabricated by the company, and we will place all the components together. So we see this is a place for jumper wires where we have two pins, one is going for ground, one is going for the supply, positive supply. These are the two resistances which we are using connected in this way, and these are two capacitors C1 and C2. We have used different form factors of all these components just to explore that we can use different type of footprints. However, choosing of these footprints are very critical. We need to stick to our electrical specifications and thermal specifications to find out the best possible footprint for our PCB. So this is how the complete footprint or complete PCB will look like with all the components placed, and this is the actual PCB. For the fabrication, we go to Fabrication Output and click on the Gerber. These are the files which you need to send to the manufacturer to make it fabricated. You can give it an example _4, any directory name, and inside that directory all these Gerber files will be produced. So you also need to generate these drill files. So click on generate drill files, close, and then plot. So all these Gerber files will be available in this output directory. You can specify the path. If you want a different path, you can explore using this button here and specify the complete path. Inside that folder you will have all the Gerber files available from the software, and you can directly send it for fabrication. So today we saw that we use a 555 timer in the stable mode. We are using multiple components along with it to make it a stable oscillator or waveform generator. The important thing which we learned today is that the graph of the circuit is not planar. It means we cannot route all the traces in a single layer, and we have to go to the another layer to route the trace. So we had one trace, let's say top to bottom, and one trace we need to write from left to right. That time we cannot have it in the same layer. We put the vias, so we take one signal through the via to the another layer, route it there, and then bring it back to the front layer or wherever we want to route it. Another important thing while designing these multi-layer PCB is whenever we are using these vias, they are a interface to the signal. When signal is traveling in a trace, the signal does not reflect at some intermediate point. The signal reflects only at the interfaces where this track either bends or it terminates with some other shape and size of footprint or pad or anything. Wherever the shape of this track changes, that interface act like a boundary and the signal will reflect. Our whole emphasis during PCB design, especially for the high speed PCB design, is signal should not get reflected. So it means we do not want to have multiple vias in the path of signal. However, if it is a complex PCB, 100 components or more, that time it is not possible to make it in a single layer. So we need to decide first which are the fast moving signals in that PCB. Let's say only 3-4 signals are there, 3-4 traces are there which are fast moving. Those traces we want to have on the front layer, and rest of the traces, rest of the signals which are not so fast moving, very slow, let's say kilohertz range, that signals we can have routed in various layers through these vias, because the low frequency signals will not face such reflections from these interfaces. So this is the technique we use for high speed circuit designs. So today we saw a circuit right from the very starting, very scratch abstract level, and we complete the complete PCB for this 555 S-stable multivibrator. So, this is all for today. Thank you.